So for number one, there's not a lot to explain. We're just matching functions with their graphs. Um, X squared, yeah, so let's think about these guys here. So this guy right here, this to me looks like square root of x. You'll notice that it's only defined for like positive x values, like it's not defined for negative x values. That's definitely a clue that it's the square root of x, which is this guy right here, number 3. B, this is the absolute value function, that like sharp v with the corner right in the middle. That's definitely very characteristic of the absolute value function. So that's this guy right here, absolute value of x. This guy right here to me looks like a exponential function, except with a b value that's less than 1. You can see that like as x is getting larger, the value of the function is going down. That's characteristic of something like y equals, say, 1/2 to the power of x. Every time you increase x by 1, you multiply by 1/2. So as x increases, as you move to the right, you're repeatedly multiplying by 1/2 again and again, and each time you multiply by 1/2, the value of the function gets smaller. So like that's very characteristic of an exponential function where the b value, like the base, this guy here, is less than 1. Whereas this guy over here, g, that looks to me like an exponential function where the b value is bigger than 1 because as x increases, the value just gets bigger and bigger. Yeah, so I think that c is associated with this guy with 5, and g is associated with 4. This guy right here, d, this looks like x cubed to me. So yeah, that's just y equals x cubed. This guy right here, that's y equals x squared. This guy right here, you probably like don't know this one very well. This is the cube root of x. It looks kind of like the square root function, except it's defined for both positive and negative values. I wouldn't worry about it if you didn't know this one. Okay, so this function right here, you're supposed to sort of compare it with these graphs here and recognize that, at least in general terms, it resembles one of them. I would argue it looks most like this one here, which is the x cubed function, but obviously it's been transformed, manipulated in some way. So I would say that in the original x cubed function, this like little point here is at the origin 0, 0, but in our graph, it's been moved 3 units to the right and 1 unit down. That's where this point is. So I'm looking for something that looks like this. Y equals x minus 3 cubed and then minus 1. So this minus 3 on the inside is going to move the graph 3 units to the right. You might remember that like when it comes to horizontal transformations, they're kind of backwards, like they're the opposite of what you would expect. Like a minus 3 actually moves the graph to the right. And then this minus 1, that's a vertical transformation because the value is outside the function, and vertical transformations behave the way that you would expect them to. So like a minus 1 moves the graph down 1 as you would expect. This is not the whole story though, because you'll notice that this graph is kind of reflected somehow, like it's backwards compared to the original one. So that to me says that there's been some kind of reflection that's happened, like it's been flipped upside down, and that there should be like a minus sign outside here. So whichever one that is over here, that should be the correct answer. Moving on to number 3, what are we doing with these problems? We're finding the x and y intercepts for each function. Cool. So for 3a, the y-intercept is really easy. You just replace x with 0. So that's going to give you y equals 0 squared minus 2 times 0 minus 35. So that's negative 35. So the y-intercept is negative 35. Technically, the y-intercept is a point. So like, you know, if we ask you for a y-intercept, we'll typically ask you to report it as a point, like with both coordinates. That's what we're getting at here. So the coordinates of the y-intercept are actually 0, comma, negative 35. For the x-intercept, you, of course, replace the y value with 0, right? It's always the other variable that you replace with 0 whenever you're trying to find intercepts. So to find the x-intercept, I replace y with 0 in the equation, so I get 0 equals x squared minus 2x minus 35. I need to solve that for x. That's a quadratic. Probably we can factor it. Pair of numbers that multiply to negative 35 and add up to negative 2. I think that's 5 and negative 7. So I think it factors like that. And then setting each factor equal to 0, I get my my two x-intercepts. So I get negative 5 and positive 7. And once again, if you want to report this answer using, like, you know, x and y coordinates, you would say negative 5 comma 0 and 7 comma 0. Okay, same story, but for 3b, I'm going to do less explanation because it's the same stuff. So x-intercept, just going to replace, or sorry, y-intercept first. So y-intercept, I'm going to replace x with 0, so that's going to give me 3 times 0 cubed minus 12 times 0, which is 0. So the coordinates are actually 0 comma 0, which is the origin. As far as the x-intercept, I'm going to replace y with 0, and I need to solve this equation. I would say that there's a common factor of x which can be removed from this expression. Actually, you could pull out more than that. You could pull out not just an x, but a 3, like the GCF. The greatest common factor is 3x. That would leave me with x squared minus 4. And this thing can be factored more because x squared minus 4 is a difference of 2 squares, so it factors as x plus 2 times x minus 2. So the x-intercepts would be 0, 0. That's coming from this factor right here. Negative 2, 0. That's coming from this factor right here. And positive 2, 0. That's coming from this factor right here. So those are the x-intercepts. 3c, y-intercept first. Again, this is pretty easy. Just replace x with 0. You get this guy right here. That's y equals root 4 minus 3. Root 4 is just 2, so 2 minus 3, that's negative 1. So the y-intercept would be 0 comma negative 1. The x-intercept, which is the much more interesting question, you obtain by replacing y with 0, which gives us this. So this is like a radical equation, like a square root equation. What we should do is we should get the square root term by itself. So I'm going to add 3 to both sides, and then square both sides. If I square the left-hand side, I get 9. When I square the right-hand side, all that happens is the square root disappears and I get x plus 4. And then so subtract 4 and I get x equals 5. So the x-intercept is 5 comma 0. Moving on, number 4, consider the function, blah, blah, blah. We'll find the x-intercepts. Oh, okay. Yeah, in this problem, we're just kind of reminding you about different ways of solving quadratic equations. This first method, we're saying, you know, solve it by using square roots. This method doesn't work very often for solving quadratic equations. So I'll just show you what we're getting at, and then I'll sort of criticize it as a method. So what I'm going to do is I'm going to isolate this squared term right here. That's the squared term, the thing which is being squared. If I isolate that guy on one side of the equation, like if I add 1 to both sides, and then I divide both sides by 4, I get this. And look at that. I've isolated the squared term on one side of the equation, and on the other side of the equation is a number. You can't always do that. Okay, you can't always do that. Let me just point out, like, most quadratic equations, like if we go to the quadratic equation we had to solve earlier, like this one right here, if you try to solve this quadratic equation by isolating the squared term, you would obtain 2x plus 35 equals x squared. Like, okay, cool. And then what? Well, the thing is, in this equation, because the left-hand side is a number and the right-hand side is a squared term, you can solve this equation by taking the square root of both sides. So in this equation, if I take the square root of both sides, I get plus minus square root of 1/4 equals just x minus 3. And then I add 3 to both sides, and I get plus or minus square root of 1/4 plus 3 is equal to x, and I can simplify that solution a little bit, but that's basically the answer. I just want you to notice that that doesn't work in this equation here. Like if you try to take the square root of both sides in this equation, you get plus or minus square root of 2x plus 35 equals x. Like, okay, but that doesn't isolate the x, does it? Like that doesn't get the x by itself. So I just want to emphasize here that this first method that we're talking about, solving quadratics by taking square roots, it only works if it's possible to get the squared term, the thing which is being squared, on one side of the equation with a number on the other side of the equation. Over here, when you isolate the squared term on one side of the equation, you don't have a number on the other side, but rather an algebraic expression. And so this method of solving by square roots, like, it's nice when it works, but I just want to emphasize, like, it usually doesn't work, okay? Like, most quadratic equations cannot be solved by this method. Anyway, simplifying this guy a little bit, when you take the square root of a fraction, that's the same thing as taking the square root of the top and the bottom. So that's plus or minus 1 over 2. Plus 3 equals x. So that's, 1 half plus 3 is 7 halves. And negative 1 halves plus 3 is 5 halves. So those are your solutions. As far as method 2 goes, what we're asking you to do here is, instead of isolating the squared term and taking the square root of both sides, we're saying put it in standard form, like multiply everything out, and then use the quadratic formula. So this is definitely a longer way of doing the problem. So to get it into standard form, first you're going to have to expand this guy. So if you multiply the x minus 3 squared out, that's x squared minus 6x plus 9 minus 1. And you have to do that before you distribute the 4. It's a PEMDAS thing, like exponents before multiplication. And then if I distribute the 4, I get 4x squared minus 24x plus 36 minus 1. Combining those two constant terms, I get plus 35. Now, at this stage, ordinarily I would try to factor this, but, I don't really know how to factor that. I mean, I guess you can. Honestly, when I'm trying to factor a quadratic, if the lead coefficient, like right here, isn't 1, like if it's a 4, and I can't pull out any common factors, I just use the quadratic formula. So that's x equals opposite of b, so b is negative 24, so positive 24 plus or minus square root of b squared is 24 squared minus 4 times a, which is 4, times c, which is 35. My god. All over 2 times 4. So that's x equals 24 plus or minus square root of, what is this, 24 squared minus 4 times 35. That's 16, miraculously, all over 8. So that's 24 plus or minus 4 over 8. So my two answers are 28 over 8 and 20 over 8, which of course those guys can be reduced, right? So I think that's 7 over 2 and 5 over 2, which is what I got before, right? Cool, good. All right, number 5, blah, blah, blah. Okay, at what value of x is this function undefined? At 0. At x equals 0, because if you plug in x equals 0, you get a 0 in the denominator, and that's like dividing by 0. That's undefined. What is f of 1? What is f of negative 1? Plot the points. Yeah, I guess I'll do that. All right, so f of 1 is 1, so that's going to give me this point. F of negative 1 is negative 1, so that's going to give me this point here, I guess. This grid seems kind of weird, whatever. Cool. What happens as you move right from 1, 1? What is f of 2, f of 4, f of 8, f of 100? Look, the function's getting smaller, right? Like f of 2 is a half, a fourth, an eighth, 1 over 100. The graph is getting smaller and smaller, like the y values are getting closer and closer to 0. So I would say what's happening is, the graph is getting closer and closer to the x-axis, and you have a horizontal asymptote at y equals 0. So to answer this question here, what is the limit as x approaches infinity? Remember that's asking like what is happening to the value of the function as x gets bigger and bigger and bigger. It's 0 because the y values are approaching 0 as x gets bigger and bigger and bigger. Okay, well now what's happening is you move left from -1, -1. What's f of -2? It's -1/2. What's f of -4? It's -1/4, -1/8. Those values are also getting closer and closer to 0, right? Like -1/2, -1/4, -1/8, etc. So the graph is also approaching 0 as you go over in that direction. So as x approaches -infinity, the value of the function is also approaching 0. Okay, now what's happening as you get close to 0? What is f of 0.5? Well, that would be 1 over 0.5. That's going to be 2. What is f of 0.1? Just to kind of be clear here, 1 over 0.1, you might wonder what that is. If you multiply top and bottom of that fraction, you get 10 over 1, so that's 10. Okay, that's 10. What is, and then they ask, what is f of 0.01? Well, 1 over 0.01, if you multiply top and bottom by 100, 0.01 times 100 is 1. That's actually 100. All right, so as x gets closer and closer to 0 from the right, like 0.5, 0.1, 0.01, the y values of the function are getting bigger and bigger in the positive sense, like 10, 100, 1,000, etc. And so the graph, as you get closer and closer to 0, is doing something like that. It's so when they ask what is the limit as x approaches 0 from the right, that would be positive infinity. Same thing from the left. It's the same story except the values are negative. Like it's -10, -100, -1,000, that sort of thing. And so the graph is going down to -infinity as you approach from the left. So that's going to be -infinity. Okay. Cool. Does this function have a y-intercept or an x-intercept? No. No, they don't. I mean, if you try to find the y-intercept, you would replace x with 0, but you get an undefined value, so it doesn't have a y-intercept. If you try to find the x-intercept by replacing y with 0, you get 0 is equal 1 over x. How would you solve that equation? Well, to solve it, anytime you have an equation where the variable is inside a denominator of a fraction, what you do is clear denominators, like you multiply both sides by the denominator to get rid of the denominator. So I'll multiply both sides by x. On the left-hand side, well, I have 0 times x, that's just 0. I mean, 0 times anything is 0. On the right-hand side, 1 over x times x is 1. You get 0 equals 1. That's not true. That's a contradiction. That's telling you that the equation you started with has no solutions. Okay, so this thing doesn't have an x-intercept either. Okay, so moving on to number 6. Consider another rational function, blah, 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 from the graph. What is the y-intercept? Looks like it's 0, 3, right? Ugh. That's too small. Let's do that. 0, 3. Find the y-intercept algebraically, like using the equation. Okay, well, to find the y-intercept, I would just replace the x's with zeros. So 3 times 0 minus 24 over 4 times 0 minus 8. That would be -24 over -8, which is, yep, that's 3. Cool. From the graph, what is the x-intercept? Looks like it's 8, so probably 8, 0 would be, like, that's definitely what it looks like. Okay, find the x-intercept algebraically. To do that, we take the equation and replace y with 0. So I obtain this guy here. Again, if you ever have to solve an equation where you have variables in denominators like I do here, all you need to do is multiply both sides of the equation by that denominator. Just multiply both sides by the denominator, and that will eliminate the variable from the denominator. So I'm going to multiply both sides by 4x minus 8. When I multiply the left-hand side by 4x minus 8, nothing happens because 0 times anything is still just 0. when I multiplied this guy by 4x minus 8, the 4x minus 8 cancels, right? Like if I do that, then this 4x minus 8 times that 4x minus 8 in the bottom there, they cancel. And I'm just left with 3x minus 24. So 24 is equal to 3x, meaning that x is equal to 8. Cool. From the graph, what is the equation of the vertical asymptote? It's x equals 2. I mean, it's a vertical line. Vertical lines have the form x equals a number, so it's x equals 2. How would you find your answer to e from the original function, shown algebraically? Well, vertical asymptotes basically occur. This is a little bit of an oversimplification, but they occur when the denominator is 0 and the numerator isn't 0. There's kind of a tricky thing. I mean, sometimes people just say, well, anyway, look, the denominator is 4x minus 8, and if you set that equal to 0, then you get x equals 2, which is indeed the vertical asymptote. The only reason that I'm kind of like hesitating in my explanation there is that you might remember from last year that if you have something like, let's say, x squared minus 4 over x minus 2, you might look at this function and say, oh, this guy has a vertical asymptote at x equals 2, because if I plug 2 into the function, I get 0 in the denominator. Well, actually, not exactly, because if you factor the top and the bottom, then you get this expression. And, if you plug 2 into this function, you actually get 0 over 0. 0 over 0 doesn't really mean anything. 0 over 0 doesn't mean vertical asymptote. It doesn't mean whole necessarily either. If you get 0 over 0 when you plug in a value, it just means that you need to do more investigation. It means that you need to rewrite or simplify your function and try plugging in again to actually figure out what's going on. So when you plug 2 into this function, you get 0 over 0. That just means you need to simplify this guy. Of course, how do you simplify it? Well, the x minus 2's cancel, right? So the simplified version of this guy is x plus 2. And if you plug 2 into that, you just get 4. Which is a regular, well-defined actual number, which is telling you that it's not a vertical asymptote. Okay, so the real story about like when do you have a vertical asymptote, it's really like, it's when you get a non-zero number over 0, right? Like if I plug 2 into this function here, into the original function that we're looking at on the worksheet here, I get 6 minus 24, that's negative 18 over 0. So as you can see there, you get a non-zero number over 0, and that's really what tells you that you have a vertical asymptote. Okay, so that's all I'm trying to say there. Finally, how do you find the horizontal asymptote? The thing is, finding the horizontal asymptote of any function, what you do is you take the limit as x approaches infinity of that function. Like, that's how you find horizontal asymptotes. And there's a whole section in the worksheet later on about finding limits as x goes to infinity. So I don't want to say too much about this right now. If you don't remember how this works, then I would just go forward, like in the video, to whatever exercises it is. It's, where is it? It's like, I know it's on here somewhere, right? Yeah, like these guys. I'll talk more about limits as x goes to infinity in this section. So if you really need like a refresher on how this works, I would go there. I'm not going to say much here. Anyway, the fastest growing term in the numerator is 3x, fastest growing term in the denominator is 4x. The x's cancel and you get 3/4. So that's the horizontal asymptote. The equation of the horizontal asymptote is y equals 3/4, right? Because that's a horizontal line. Okay. All right, moving on to part 2. So number 7, we're doing some trig. This is just asking you to evaluate different angles. 7 pi over 3, that's kind of a nasty one to start with, isn't it? 7 pi over 3 is not like a regular unit circle angle. The reason why is it's too big. Like 7 pi over 3 is bigger than 2 pi. Like that's actually it's pi over 3 bigger than 2 pi, because 2 pi with a denominator of 3 would be 6 pi over 3. Do you know what I mean? So like this angle is actually a 1 pi over 3 bigger than 6 pi over 3. So in other words, it's coterminal with just regular pi over 3. So like, yeah, 7 pi over 3, that's basically the same angle as regular pi over 3. So we're really just asking you for cosine of pi over 3. You know, how do you think of that? Well, I don't want to review trig too much, but basically pi over 3, the x-coordinate is small and the y-coordinate is big. So I know the x-coordinate is 1/2 and the y-coordinate is square root of 3 over 2. So the cosine is 1/2. Okay, so the cosine is 1/2. B, cosecant, like I don't know any cosecant values. Nobody does. Nobody remembers cosecant or secant values. What you should do is you should just remember that cosecant is like the reciprocal, like the flip of sine, right? So if I have to find cosecant 5 pi over 3, I know that I just need to do 1 over sine of 5 pi over 3. Sine of 5 pi over 3, I know. That's, let me think about that. That's going to be in quadrant 4, like the bottom right quadrant. And the sign is negative in that quadrant, so it's going to be negative something, negative root 3 over 2. Okay, of course, you know, 1 over this guy just flips that thing upside down. So it's going to be negative 2 over root 3. And that's okay. Oops. That's okay, except you should rationalize that denominator. So that's going to give you negative 2 root 3 over 3. Okay. C, tangent 5 pi over 6. If I think about where that angle is, it's, you know, sort of like over here. The tangent, which is the slope of that line, is definitely going to be negative, so it's going to be negative something. I know that tangent 5 pi over 6, let me think, that's either root 3 or like negative, or root 3 over 3. Root 3, you know, you might remember, like, you might remember that when it comes to tangent, tangent 5 pi over 6, sorry, tangent of pi over 6 looks like this, and tangent pi over 3 looks like that. You might forget which one is which. One of them has a tangent of root 3, and another one has a tangent of root 3 over 3, and you might forget which one is which. Just remember that root 3 is larger than root 3 over 3, obviously, because like when you divide root 3 by 3, it gets smaller. And tangent is just the slope of the line. So, you know, which of these two guys has a larger slope? Well, this one does. That's pi over 3, okay? So this has a tangent of pi over 3. This guy has a tangent of, sorry, this guy has a tangent of root 3. This guy has a tangent of root 3 over 3. So that's pi over 6. So I know that tangent 5 pi over 6, which is over here, is also basically going to be root 3 over 3, but it's going to be negative. So it's going to be negative root 3 over 3. Okay, so D, sine of negative pi over 4. Yeah, I mean, so, you know, sine of pi over 4, it's going to be either positive or negative root 2 over 2. Where is negative pi over 4? It's here, and the y-coordinate's negative down there. So that's going to be negative root 2 over 2. E, secant 5 pi over 4. So once again, anytime I need to find secant or cosecant or whatever, I just look at the reciprocal function. Secant of 5 pi over 4 just means 1 over cosine 5 pi over 4. So what is cosine 5 pi over 4? Well, it's either positive or negative root 2 over 2. The only question is, like, where is 5 pi over 4? 1 pi over 4, 3 pi over 4, 5 pi over 4 is down here, okay? And the x-coordinate of that guy is negative, so that's going to be negative root 2 over 2. So keep it, change it, flip it, like the 1 over this fraction flips it upside down, so that's negative 2 over root 2. And now if you rationalize that denominator by multiplying top and bottom by root 2, you get negative 2 root 2 over 2, and then this 2 here cancels with that 2 there, and you just wind up with negative root 2. Finally, f, negative 7 pi over 6. Yeah, like negative angles, I usually think about like where is the positive version of that angle first. So like 7 pi over 6, like that's not a very good circle, but I'm drawing on a trackpad. So 7 pi over 6, like positive 7 pi over 6 is like here. It's like wow, down to here. That's positive 7 pi over 6, which means negative 7 pi over 6 is actually going to be like here. Okay, so that's a pi over 6 angle in that second quadrant over there. Again, as far as cotangent, like I would just find the tangent and then flip it upside down. So I'm really doing like 1 over tangent of negative 7 pi over 6. Okay, now tangent of 7 pi over 6. Well, I know we talked about this earlier. Any kind of pi over 6 angle is going to have a tangent of either positive or negative root 3 over 2. Which one is it here? Well, in this quadrant, tangent is negative because tangent just means slope, and this slope is negative. So that's negative root 3 over 3. Okay, and so 1 over negative root 3 over 3. If you flip this guy upside down, that's going to be negative 3 over square root 3. And if you multiply top and bottom by root 3 to rationalize, then you get this guy, and then the 3's cancel, and you just get negative root 3. Okay? Cool. Number 8, we are factoring. Okay, so this very first one, like problems where the lead coefficient isn't 1, that tends to be more annoying. Like I can't pull anything out of all 3 of these guys. Everybody has different methods for factoring these. Maybe you like guess and check, or you do the box, or whatever. My preferred method is to split the middle. Like, so I'm looking for a pair of numbers that multiply to 2 times negative 9, which is negative 18, and they add to 3. So what pair of numbers does that? Let me think about that. That would be negative, that'd be 6 and negative 3. Right? So what do I do with those 2 numbers? I split the middle. Like I rewrite the middle term. I rewrite 3x as plus 6x minus 3x minus 9. Then I pull the GCF out of these 2 terms and these 2 terms. So 2x quantity x plus 3. And I'm going to pull a minus 3 out of the second 2 terms. And then I have a common factor of x plus 3 here and here. If I pull it out, that leaves me with this. That's how I factor this. Not everybody does it this way. Like, I prefer this method because it doesn't involve as much like guessing and checking, but whatever. If that method is unfamiliar, like then use the box or whatever makes you happy. It doesn't really matter. Okay, so 8b, we have 6x to the 4th plus 30 x cubed plus 36x squared. There's a common factor that can be removed here. All the terms are divisible by 6, and also I can pull out an x squared. So if I remove 6x squared from each of these, I think I'm left with x squared plus 5x plus 6, and that second term in parentheses. Because the lead coefficient is a 1, I just need a pair of numbers that multiply to 6 and add up to 5. That's 2 and 3. This guy factors as x plus 2 times x plus 3. Voila. 8c. You could view that as a difference of 2 squares right off the bat, or you could say there's a common factor of 4 that you can pull out like that. And then that x squared minus 4 factor, it's a difference of 2 squares. That's x plus 2 times x minus 2. So that's how that guy goes. 8D, again, it's another one of these problems where it's a quadratic, but the lead coefficient is not a 1, so it's kind of annoying. I'll once again do the method that I talked about before, splitting the middle. So I'm going to look for a pair of numbers that multiply to not just 5, but 5 times 3, which is 15, and add up to the middle term, which is negative 8. So what numbers would multiply to 15 and add up to negative 8? That'd be negative 3 and negative 5. What do I do with those numbers? I split the middle, like I rewrite that middle term. Negative 8x, I rewrite it as minus 3x minus 5x. And then I pull the GCF out of these two terms, which is 3x, which leaves me with x minus 1. And I'll pull the GCF out of these two terms. There's not much to pull out. Or yeah, there is. I can pull to minus 5. Minus 5 times x minus 1. And then I have a common factor of x minus 1 here and here, so I'll remove that. X minus 1, and what I'm left with is 3x minus 5. There we go, voila. But once again, like if you do a box method or whatever, it's fine. Okay, number 9. Yeah, so 9a, I mean, you know, you multiply these coefficients and you add the exponents, right? So that's 30x to the 7th. 9b, you know, I would say two things. I mean, first of all, the 12 over 24, that can be reduced to 1/2. And then the x's, there's x's on top and there's x's on bottom. There's going to be a lot of cancellation, okay? After you do the cancellation, there's going to be only one copy of x left over. Where is that leftover copy of x going to be? It's going to be in the bottom because there are more copies of x in the bottom to begin with. So there it is. 9c, because of these parentheses, this exponent of 4 is being applied to everything, like the coefficient 3 included. So it's 3 to the 4th times like x squared to the 4th. 3 to the 4th is 3, 9, 27, 81. And then x squared to the 4th, you multiply those exponents, so that's to the 8th. 9d, I would start, I mean, so there's a few things going on here. I mean, for one thing, the 3 over 9, you can just reduce that, right? That's 1/3. So let's just do that. After that, I would say the negative exponents, remember negative exponents in a fraction mean they sort of like move around. So like this x to the negative 2 is going to go downstairs and become an x to the positive 2. Likewise, this x to the negative 4 is going to go upstairs and become an x to the positive 4. Now I'm ready to just do some cancellation. There are x's on top and bottom. I'm going to do some cancellation. How many copies of x are going to be left over? 2. Where are those leftover copies going to be? Upstairs, because there were more copies of x to begin with upstairs. So I think it's just 1x squared over 3, which is just the same thing as x squared over 3. Okay. All right, more like exponent simplification stuff. I mean, for a, you're just going to subtract those exponents. Like that's x to the power of 7/2 minus 3, which is x to the 7/2 minus 6/2, so 1/2, which is the same thing as square root of x. 10b, I think we need to multiply everything out. So 3x to the 4th times 2x to the 3rd, that's 6x to the 7th. 3x to the 4th times 5, that's 15x to the 4th. 2x squared times 2x to the 3rd, that's 4x to the 5th. 2x squared times 5, that's 10x squared. That's basically it. Are there any like terms to be combined? No, because they all have different exponents. This guy here, 10c, I think you need to rewrite this using like fractional exponents. The cube root of x squared, I mean, we have like a 5/2 of this. We have like a 5/2 on the outside here. The parentheses look a little weird in this problem, don't they? Like, I don't think this outside set of parentheses is supposed to be there. Right. Just pretend it's not there. Yeah, so we have like a 5/2 on the outside. The thing inside the parentheses, like the cube root of x squared, that's the same thing as x to the 2/3. And so now you have a power of a power, and so you multiply the exponents. So that would be 10/6, which is the same thing as 5/3. If you want to rewrite that without using fractional exponents, that would be the cube root of x to the 5th would be one way of writing that. Okay. 10d. Yeah, I mean, anything to the 0th power is 1. So just notice this 0 here only affects the x, like it does not affect the 3. Exponents by default only affect the thing directly in front of them. So like it's 3 times 1 times, and then this 0 does get applied to everything inside the parentheses. That's what the parentheses are doing. So times 1, so it's just 3. 11a, yeah, we need to get common denominators. So multiply top and bottom of this first fraction by this denominator here, x plus 3. So 3 times x plus 3, oops, over x plus 2 times x plus 3 plus, and then multiply top and bottom of this fraction by this denominator, x plus 2. So 4 times x plus 2 over x plus 2 times x plus 3. Then I think I want to distribute. So like that's 3x plus 9. And then over here, I have 4x plus 8. And now I can combine these two fractions to get 3x plus 9 plus 4x plus 8. That's 7x plus 17, I think. There's no reason to multiply out the denominator. I would just leave it in factored form, probably. 11b. Okay, x squared over 6x plus 2 times 10x plus 4 over x cubed. Yeah, I mean, you can put that into a single fraction, like multiplying the denominators and the numerators, like this. I think there's some cancellation you can do, like this x squared here is definitely going to cancel with 2 of the x's here. Let's just take care of that. So I just have 10x plus 4 in the numerator and 6x plus 2 and then just an x there. That's a little bit better. I think there's some common factors that can be pulled out of this guy and this guy though. Like in the numerator, 10x plus 4, there's a common factor of 2. So that's 5x plus 2, like that. And then here, there's a common factor of 2 that I can pull out. So 2 times 3x plus 1 times x. And I guess that allows me to cancel these two 2's here to get 5x plus 2 over 3x plus 1 times x. C. I think we're probably just gonna cancel common factors or something. So the numerator factors as, so I need a pair of numbers that multiply to 6 and add up to 5. That's 2 and 3. So it factors as x plus 2 times x plus 3. Denominator factors as x plus 3 times x plus 3. This x plus 3 up top will cancel one of the x plus 3's in the bottom. So you're just left with x plus 2 over x plus 3. 11d, this is going to be annoying, not going to lie. This one's going to be painful because it's a complex fraction, like fractions inside of other fractions. What you want to do anytime you have a complex fraction is you want to get it into the form like a over b over c over d. Like you want a single fraction up top and a single fraction down below, because once you have it in that form, you can keep it, change it, and flip it, but only once you have it in that form. So right now, the denominator is not even a fraction. Like I want this to be a single fraction, so I'm going to have to combine those. That'll give me my a over b. And I want this guy to also be a fraction, like my c over d, but it's not right now. That's okay, I can make it into a fraction, right? So the x plus 2, I would rewrite that as x plus 2 over 1. Now it's a fraction. And then in the numerator, to combine these two guys, I need common denominators. So I'm going to multiply top and bottom of this guy by x plus 1 and multiply top and bottom of this guy by x. So that's going to give me 2 times x plus 1 over x times x plus 1 minus 3x, right? Okay, cool. So just copying that bottom. Okay, so in the numerator, I have x times x plus 1. That's the common denominator there. And in the numerator, I have 2 times x plus 1, which is 2x plus 2. And then I have the minus 3x. Don't love how this is looking. There we go. That's better. I like to draw the larger fraction bar, like noticeably larger, to make it clear. Yeah, so I think we can simplify this quite a lot. Like, I can combine these two guys, the 2x and the minus 3x, to give me like a negative x. So negative x plus 2. Okay. Yeah, okay, so now finally this guy is in the form a over b over c over d, like one fraction divided by another fraction. And so I'm ready to keep it, change it, flip it. So, yeah, so that's going to be negative x plus 2 over x times x plus 1 times the reciprocal of the bottom one. So that's this guy here. You might be tempted into thinking that this x plus 2 maybe can interact with this guy, but they can't. The minus sign really prevents that from happening. They're just two different factors. So unless I've made a mistake, I think you just get x times x plus 1 times x plus 2 over negative x plus 2. I think that's all you can do. Okay, I think I'm going to stop the video here.